like,
okay. So the last piece, we have been talking about the least squares regression line. So that all started with our discussion on scatter plots. Then we went into the correlation coefficient. And what does the correlation coefficient tell us? How linear it is. If it's really close to 1 or -1, it's linear. If it's close to 0, it's not. And then we actually wrote the equation for that linear regression line. Today we're looking at some other things that we can tell from that line. So the first thing is the coefficient of determination. It's r squared. If you look on your formula sheet in chapter 4, this is right under residual. So this capital R squared, it tells us the proportion of variation in the response that's explained by the regression line. Okay, that sounds really weird. But what it's telling us is if we're looking at a set of data, we know that the y values are different from one another, right? Not every y value is the same. So if this r squared was 0.5, it tells us, well, 50% of the reason those y's are different from one another is explained by the regression line. You know, if your points on a line, all the y's are expected to be different. So a certain amount of that variability is because of the line. Then some of it is due to other things, like just the line not being a good match for our data, those kinds of things. It's very closely related to the correlation coefficient that we've already looked at. It turns out this is the same as just taking the lowercase r, the correlation coefficient, and squaring it for linear data only. So that's why they call it capital R, because if you were to look at nonlinear data, it's not just taking the correlation coefficient and squaring it, but everything we're doing is linear, so that's how it works out for us. So it's a very simple calculation. We're just going to square the r that we've already been finding. It's giving us a percent, so it will be something between 0 and 1. It'll be positive because we're squaring. So if it's close to 0, then it's saying the line doesn't explain any of the variability. Kind of related to if the r is really close to 0, we know it's not linear, so we wouldn't expect the line to explain the variation. Close to 1 means it's really good, so 1 is 100%. So the line is a perfect match for the data. The line explains all the variability in our data. It's essentially, we're talking about deviation, which is just how things differ from our mean. And we're looking at two different things, explained and unexplained. So explained is when the variation is explained by the regression line. And unexplained is when there are other factors, like I was already saying. So it might be that, you know, a linear model is just not appropriate for that data. So let's just go to an example, and we're going to work from there. So this is some data, a data set we've looked at before, the drilling data. So we have X and we have Y. So let's enter that into our calculator. We have been going into stat, calculate, number 4, linear regression. Your X should say L1, because the X is in the first list. Y should say L2. And so then we can calculate. And if yours does not have the R, what do you have to do? you have to go into your catalog and turn the diagnostics on, which is going to take forever up here. Okay, so this is where we've been going already. And you'll notice there is a number that we hadn't really been using, and it gives you your R squared. So let's go ahead and write that down. Okay, so the R squared is 0.5973. That is the coefficient of determination. And if you look at your formula sheet, it tells you exactly how to find this. You know, it has the capital R squared equals lowercase r squared, so it tells us what we're looking for on the calculator. Then the bullet underneath that says the coefficient of determination, R squared, measures the proportion of total variation in the response that's explained by the regression line. So if I ask you to interpret it, we're writing a sentence, but that little blurb on our sheet tells us what our sentence should be. So this says 59.73% of the variation in the response. The response is your Y, so that would be in the drill time. Is explained by the regression line. Okay, so you need to be able to write that sentence. And all I really did is took that sentence off your formula sheet and I subbed in the percent, and instead of saying response variable, I put what the response variable actually was. Okay. So what does that really mean? And this is really kind of telling us the same thing that R was already telling us. It's just a measure of how linear it is. So this just shows you a few different data sets. In this first data set, it's almost a perfect line. So that one, your R squared would have been 0.9999. 99.99% of variations explained by the line. It means it's very, very linear. This one is a little less great. That one is a 0.947 for the R squared, 94.7%. See, we can tell that's a pretty horrible line. That one was R squared of 0.094. That one wasn't very linear at all. So the less linear it is, the smaller the R squared will be. Really just kind of the same thing that we already were looking at with our R's. So that's the first thing that we can look at, the coefficient of determination, just R squared. Second thing we're going to talk about is residuals. You guys have already been finding residuals. What is a residual? Your observed minus your predicted. So basically, how far apart is the point from our real set and what we expected from our line? Okay, measuring those. And we know that the smaller it is, then the closer it was to our line. If the residual is really, really large, that means that point was really far away from our line. What we can actually do is graph the residuals for every point in our data set to see, again, if the linear model is a good option. So here's what residuals are useful for. Three different things. To check if a linear model is appropriate, to determine if the variance of the residuals is constant. In other words, that's meaning like, was our line really good at the beginning, but when our points get big, is the line becoming less accurate? You know, if you think about if you had a scatter plot where you know, all of our points start out like this, but then we can see the line's really good up front, but as time goes on, the line is less great for our data. So it tells us if there's something like that going on. It's also another way of checking for outliers. We know we can check for outliers if we want to go through the upper fence and lower fence process, but this is another option. So what we're actually going to do is graph the residuals. We are not going to do it by hand. It would be very time consuming. You'd have to find a residual for every single data point and then graph it. Our calculator can do that for us very quickly. And then we're going to check for these things. Okay, so when it comes time for the test on this, I might show you a residual plot and ask you, does it violate any of the conditions? And what we have to look for is patterns, constant error variance, and outliers. We don't want any of those things, and I will show you what all of those things mean as we go through. When we are looking at this, if it's linear, we are looking for no pattern. When we graph the residuals, we should not have any clear pattern to it. Because if it's truly linear, you should have some points above and some points below. Some positives, some negatives, a good mix of them. If we see a clear pattern, that means that the linear model was probably not the best thing for us. This is really just all linking in with checking if something's linear. And we already have several ways of doing that. Correlation coefficient, coefficient determination, residuals. We're giving you multiple tools to test the same thing. The reason we need that is because the correlation coefficient can sometimes imply a linear relationship when one doesn't really exist. So if we only look at that R, sometimes R is going to tell us it's linear, but it's actually not. The residuals check for this case. So it's dangerous to only rely on that R. Residuals is another thing we can look at just to make sure it is in fact linear. Especially when, you know, your R is very, very close to the critical value. Sometimes it's a little iffy. So residuals can be another thing that we look at to verify that it is linear data. All right, so I put a couple pictures of residual plots on here just to kind of show you what we're looking for. This first one is a good residual plot. There is no pattern. Okay, here's 0. We have some positive residuals, some negative residuals. It's pretty spread out. At the beginning, we have positives and negatives all the way through. So that would be linear. This one is not linear because we have a pattern. We can see at the beginning, our line was over approximating things, and then they were all negative, and then it was all positive. If you have a pattern like that, then your data wasn't really linear to begin with. So we don't want patterns. So we're going to talk about how to get a residual plot. So a chemist has a 1,000 gram sample of a radioactive material. She records the amount remaining in the sample every day for a week and gets the following data. I want to decide if it is linear. So what options have we used to see if things are linear before? We can look at R squared and R. So let's start with those. If I looked at those two pieces, so we know we just have to run our regression. All right, so the R is negative 0.9941. What does that tell me? Does it sound linear? Yeah, it sounds pretty linear. What does the negative tell us? Yeah, it's decreasing. If I asked you to check if it's linear, you would have to use the critical value in table 2, right? What would be my n if I did that? 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 points, so if n is 8, that tells me my critical value is 0.7. So is this linear according to that? Yes. So based off everything we know, that would be linear. Your r squared, it's given to you here. That's the same thing as if you just square this number. So it tells us that almost 99% of the variation is explained by the regression line. So again, that sounds really, really good. It sounds like very, very linear data. So the other thing that we can look at is our residual. All right, so we can make a residual plot in our data. If you have a book, page 219 does kind of have a summary at the bottom of how to get that. If you forget, or you might just make a note on here, page 219 in your book does tell you how to do it. All right, so now we have to look at that scatter plot. So what we're going to do is go into our stat plot. And I want to go into plot number 1. Okay, I want a scatter plot, so that's the first option. My X list, I want it to be L1. But my Y list, I don't want to plot these Y values. I want to plot the residuals. So to get that, if we go into second stat, this gives us a list of variable names, and we want number 7, residuals. So for my Y list, we went second stat, changed it to residuals. Now when you are then using this calculator later on, and you go in here, how would you, if you just wanted a normal scatter plot, what would you have to do on your Y list? And change it back to L2. Okay, so you do need to watch that now. So then if we go to zoom 9, I still have other data in my, hold on, I have my plot 2 turned on. Let me turn that off. Okay, so here's my data. Does everybody get this residual plot? So I will never make you do a residual plot by hand. If I ask you to do it on the calculator, then you would need to draw me a rough sketch of what it looked like, just so I know that you saw it. So something like that. So a good residual plot, if it's linear, you won't see any pattern. It won't violate constant error variance, which we haven't really talked about yet, and we'll have to watch for outliers. What's wrong with this? There's a pattern. That means that our line was over-approximating at the beginning, then it under-approximated everything, and then it over-approximated everything again. That's bad. So this residual plot tells me it is not linear. Even though everything else indicated it was, there is a pattern in the residuals. Okay, if you want to make a note to yourself what was happening, it was overestimating it first, then underestimating, and then overestimating again at the end. R was really indicating linear because, you know, if you averaged all of these, the average is really close to 0. But this is saying, well, that data really wasn't as linear as it appeared because our line has some flaws. I know that all my early data, the line is going to give me a value too high. All the middle data, the line's giving me something too low, and all the ending data, it's giving me something too high again. So it's not a great approximation. All right, so the next problem that we might encounter is constant error variance, which I kind of talked about here, that as time goes on, your line might be a worse approximation. And we see that here. This is my residual plot, so we can see the residuals started out pretty close to 0, but then as time goes on, they just get more and more spread out. That's a little bit obvious looking at this line of best fit, but not as clear. We can see at the beginning most points are fairly close. They got a little more spread out as time went on, but didn't seem that obvious until you looked at the residual plot. And it could be vice versa. It could be at the beginning they're really spread out, and as time goes on it gets better. But in a true residual plot, we just want like 2 flat lines. Okay, if you have like a cone shape, that's the constant error variance that we don't want. What that means is that the line is less accurate as time goes on. The last thing that we can look at with our residual plot is just to check for outliers. We know what it looks like on a box plot. With a scatter diagram, we know an outlier kind of looks farther away. Again, with this scatter plot, it's not as obvious, but when I look at my residuals, all of my residuals fall in here except this one way out to the side. So it's just another way you can watch for any outliers that might happen if you plot your residuals and you have a point really far off, just like we've seen with scatter plots and box plots. All right, so I want to, I should have done this example first, but let's do the residual plot for the drilling data. So sorry, I should have done that one first so you didn't have to clear out your calculator and put it all back in, but just for fun, let's do that. We go into our stat plot, and we shouldn't have to change anything because right now my stat plot is turned on, and we see my X list is L1 and my Y list is residuals already. So then if you just zoom number 9, uh-oh, what did I do? Did I mistype something? Did your alls work?
Yeah.
Yours did the same. I know why. Okay, good point to bring up. So your calculator does not store the residuals unless you run the regression line. So right now, it's trying to graph residuals from our previous example because that's the last time we ran the regression line. So we need to go into, even though I didn't ask you for your R or your R squared, we have to go into our stat, calculate number 4, the linear regression. And you'll have to do this anytime you change your data set. So even though I'm not writing any of this down, now our calculator has stored it all. So now we should be able to go into our stat plot, and we already have that turned on to residuals, so we can zoom 9. And now we've got it. Okay. Does it have any outliers? No outliers. Does it have a pattern? Not really a pattern. Does it violate constant error variance? Maybe. It does kind of look like as time goes on, it's spreading out a little bit, doesn't it? They start out pretty closely, but then it widens over time. So this one has the constant error variance. It's not horrible, but it's probably not a great model. Okay, you're not going to have perfect plots, but constant error variance is a concern with this one. So on your notes, if you wanted to jot that down, just draw yourself a rough sketch of that scatter plot and you could point that out. All right. I'm almost done. One last thing we're going to talk about. So we know that sometimes we're going to have outliers. We have to look at if an outlier is influential or not. So by influential, I mean how much does it change our regression line? All right, so this scatter plot, we're looking at it. It's a regular scatter plot, and we have 3 outliers here. 1, 2, and 3. I have a mark for you. So I want to know which of these would be influential points. So influential means when you did the line of best fit, it would change your line a lot. All right? Do you think the first one would change our line? Yeah, it's a lot higher. So this one is an outlier. It would have some impact on our regression line. So it is somewhat influential. What about this one? No, if you did your line of best fit, it's probably going to go right through the middle here. Is that point really that far away from the line? No. No. So this one's an outlier, but it's not going to be influential because it follows the pattern. What about this one? Yes, this is definitely an outlier. It would be influential. It's not going to fall in line with my line of best fit. Sometimes we might just look at the lines of best fit. So I might give you, some data and say, okay, this first line is the line without an outlier, and then I did a line with an outlier, and I got this. Is there a big difference between those lines? There's some, and we expect some, but is it real significant? No. So in this case, would that outlier be influential? Not really. It minimally changed our line. But I might give you another case where I said, okay, so I had some data, that was the line of best fit, and then I did my line with the outlier, and my line looked like this. Is that influential? Yeah. So you could look at it from the scatter plots. A lot of times though, I think even on the homework, it gives you like pictures and has a line with and without a point. And you're looking, if those lines are fairly close to the same, it wasn't a big deal. But if those lines change a lot, it was a big deal. It was influential. So let's try that with our drilling data that we already have in the calculator. I want to add another point and decide if that is influential. So we'll go to our our stat edit, and we just need to add this on. What would be the x value here? 300. My calculator froze. You guys may have to do this without me. We'll see if it comes back. So add that point on your calculator. 300 for the x, 1249 for the y. I should have had you write down first, and I didn't. So my calculator, I haven't deleted out my original yet. So the linear regression line with the original data we had in here was 0.0116x plus 5.5273. So that was my original. All right, you guys have entered that point. So now go run your regression line. And tell me what you get. Okay. So I'm at this point and I was trying to decide if it was influential. If you just compare these lines, does it appear to be a big difference? Doesn't really look like it. Another way you could check is actually graph both of those lines. If you go to your y equals, for whatever reason my calculator is freezing, so it's not letting me do anything. If you go to your y equals, you could graph both of these two lines and see how far apart they are. And that might be a little bit easier than just trying to look at the equations themselves. You'll want to make sure you turn off your stat plot when you graph these so that you can actually get a clear picture of the lines. And when we graph it, we probably need to reset our window because we're zoomed in to plot residuals. So you'll need to go to zoom number 6 to kind of reset that window. So that's my first line. And this is my second line. You can adjust the window and kind of look at them differently. Some of this is somewhat of a judgment call. You know, sometimes they're really, really close together. Sometimes they're really, really far apart. A lot of times it's somewhere in the middle. So just make sure you can justify your answer. Okay, there's not always a clear cut, yes, those are far enough apart, or no, these aren't. You have to kind of decide there. Okay. Questions? All right. So I know I taught the whole day today. So we will have a work day tomorrow for this section. So you will need to bring your textbook to class tomorrow.